And then if I go back to this menu and I try to click start recording again, oh, it's working now. See, it knows because I was talking about it. Because earlier I would go back here and instead of stop recording, it still said start recording, but it wasn't, I couldn't, it was already like highlighted. I couldn't touch it. So, okay, good. At least it's working now. Okay, so let me go back to Canvas. All right, so the second part of topic 15 has to do with spontaneity of chemical reactions, okay? So in your 3 videos today, it's going to kind of introduce what is spontaneity, and then it's going to talk about this concept called entropy, okay? And it's like, what is it? And then how do we perform calculations with it, and what things affect it? So entropy has to do with like chaos and disorganization. And so the more organized things are, the less entropy there is. The more disorganized or the more chaotic things are, the more entropy there is. So in terms of chemistry, this has to do with kind of like the particles and the motion of the particles. So in one of the videos, and this is the part that wasn't in your notes that I told you guys you'd probably have to add in when it talks about the factors that affect entropy. Things like state of matter, because if you think about what the particles in a solid look like, they're very like organized in that like grid pattern, locked in place. So they have very low entropy. And then as you change to a liquid and then to a gas, they spread more further apart. They gain energy. They're moving. They're more chaotic because they're moving more. And so as you go from like solid to liquid to a gas, you're increasing the entropy. Okay. And then so phase changes affect the entropy. Dissolving things, because if you dissolve something, just like we talked about with lattice energy, we're going from, and the enthalpy of hydration, I'm going from a solid ionic compound that's highly organized in its crystalline structure, so that's super low entropy, and then I'm dissolving it, so I'm going through the lattice enthalpy change because they're becoming the gaseous ions, and then they're being hydrated into the aqueous solution, so they're free to move around more in the solution. So if I dissolve something, that increases the entropy as well, okay? It also talks about in chemical reactions, if you're talking about things like gas particles, if you're looking at like the reactant and product side and you're trying to figure out which side has higher entropy, the side with more gas more moles of gas is always going to have more entropy, because if I have 2 moles of gas on one side and 3 on the other, 3 moles is more than 2, and gases increase entropy. So the more gas you have, the higher your entropy. And there's a 4th thing, but like I'm forgetting it off the top of my head right now. Oh, I think it was just the related to the phase changes about, you know, like melting is going to increase the entropy because I'm going from a solid to a liquid, and so would boiling. But if I go the opposite way, that's going to decrease the entropy because things are getting more organized. Okay. So your 3 videos, the first one talks about what a spontaneous process is, because spontaneity, that's like naturally occurring. So they use this analogy of like a rock or a ball going down the hill, because that's spontaneous because of gravity, right? But the ball is not going to go up the hill unless we put some kind of energy into it. We would have to put some force behind it and like to go up this hill against gravity. And so spontaneity and entropy have to do with that, because spontaneous processes are usually going to be exothermic. They're more likely to happen without us having to add in any kind of energy. Non-spontaneous, those are going to be more like your endothermic, because you're having to put in some effort to get them to happen. Okay. This is where they talk about the changes. How do you predict changes in entropy and what things affect it? So like here, you know, they're saying this equation from liquid to gas. So liquid to gas, you're increasing the entropy because your particles are becoming less organized. And so you have a positive entropy change. And entropy, as you probably have seen in the video, it's represented by this capital letter S. That's the letter for entropy. Just like enthalpy is the delta H. Okay. But here backwards, gas to liquid, now I have negative entropy because I'm becoming more organized when I go that direction. Okay. And then the last part is how then do we calculate what we call the standard entropy change of a reaction. So this is really similar to when we did enthalpy. Okay, the equation looks pretty much the same. It's just we have S's in here instead of H's, because but you still do the total of the products minus the, oops, I didn't mean to click play. Go back. You still do the total of the products minus the total of the reactants. Okay. So I'm going to switch over to the iPad so we can kind of look at stuff really quick. So have you guys watched those 3 videos? Yes or no?
Yeah.
No.
No? Okay. Jennifer?
No.
No. She's like, no. Like, she's laughing. Oh, there we go. I was trying to get the iPad to come up. Oh, Brandy's here. Hi, Brandy.
Hi, Miss.
I didn't see you pop in. Okay. All right. So in 15.2, I kind of split it in half. So the first part, we're talking about the spontaneity and entropy. The next part that we'll get to next week is this Gibbs free energy. And this is the only one that makes sense because look, it's a G for Gibbs. Okay. Enthalpy is H, and Gibbs free energy is G. Okay. And so all of these things are going to eventually relate to each other, because if you see here next week, we're going to have this equation where we can calculate the change in Gibbs free energy by using the enthalpy change, the temperature, and the entropy change. Okay. So eventually all this is going to come together next week when we do the Gibbs free energy. All right. So you guys kind of saw in the video, they talk about this spontaneous thing. One thing I want to point out, and he mentions this in the video too, spontaneous does not relate to speed. Okay. So for example, lighting a Bunsen burner, that's exothermic because it's giving off heat. So that's spontaneous because all I had to do was allow the methane gas to react with the oxygen, okay, and give it a spark, okay. That's spontaneous, and that's really fast because, you know, we can hear the gas and the flame coming out of the Bunsen burner, okay. Over here, we got rust. Rust forming is also a spontaneous process. It's just a really slow one. So a lot of people, like, you think of spontaneous as like, oh, you just don't have any plans and you just go do something really fast. Well, in chemistry, spontaneous doesn't have anything to do with the speed at which a reaction happens, okay? It's just talking about the enthalpy and the energy. So something that is like this one, the spontaneous, that's where we're going to have exothermic because we're going from things that are we're going to make things that are more stable, okay? So it's more likely to happen. Non-spontaneous is just less likely to happen because we're going to kind of going against the grain, okay? All right, so I kind of already mentioned that entropy, it's the distribution of available energy among the particles. So that's why it has to do with, when I say it has to do with like chaos or disorganization, really this is the technical thing here. The distribution of available energy among the particles. So if your particles are very rigid, like in a solid, okay, the entropy is going to be low because of how they're organized and how that energy is distributed. When you change to a liquid and then to a gas, they're getting more disorganized, and so the energy is going up between them, okay? So it says the more ways the energy can be distributed, the greater the entropy. Gases have higher than liquids, which have higher than solids, okay? And then I talked about in your videos, make sure when you watch them, because they go into a lot more detail about the things that affect entropy, not just the state of matter, but they talk about the phase changes, they talk about dissolving, they talk about the gases and the chemical reactions. So all that stuff is not on these pages. So I told you guys that you could add them in like on your own paper and just kind of stick them in between, like you could stick it in like between page 10 and 11 in your notes or something like that, okay? So there are some practice exercises in here. So I want to look at number 2. Okay. So number 2 says, which change will not increase the entropy of a system? So that means 3 of these are going to cause entropy to go up. 1 of them is not. So look at our answer choices. We're going to check all of them. So letter A is increasing the temperature. So do you guys think that will or will not increase the entropy of a system?
It will.
Well.
Why will it?
Because it could change the state.
Yeah, exactly. Because increasing the temperature usually implies you're changing the state. And even if you're not changing the state, even if it's just going from, even if it's a gas and you're just making the gas hotter, the higher, remember, temperature is related to kinetic energy, right? They're directly proportional. So increasing the temperature is going to make the particles move faster. And that means there's more entropy because there's more ways to distribute that energy to the particles. Okay. B says changing the state from a liquid to a gas.
Yes.
So, okay, and that's kind of that's kind of related to A, because when we change from a liquid to a gas, we are increasing the temperature and the particles are moving apart. Okay, there's more ways to distribute the energy because they're moving more. All right, C says mixing different types of particles. What do you guys think on that one? So different types of particles. So we're talking like, maybe some ions, maybe some covalent stuff. We're mixing different things together. Does that sound like it's going to be very organized?
No.
No. So anytime you're mixing different things together, that's not really organized. That's causing more chaos, more disorder. So there are more ways to distribute that energy. And so that one will increase it too. So by process of elimination, it must be D. And if we read D, it says a reaction where 4 moles of gaseous reactants changes to 2 moles of gaseous products. That one will not increase it. That one will decrease it. Because when you watch the videos and they talk about chemical reactions and the state symbols in chemical reactions, they talk about whichever side of the reaction contains more moles of gas, that's where the higher entropy is. So if I'm starting with 4 moles on the reactant side of gas, but on the product side, I only have 2 moles of gas because maybe my other 2 are going to be solid or liquid or something. I don't know. It just depends. Then that would lower it because you went from 4 to 2. So less gas particles, that means less ways to distribute the energy. Okay. So there's a few other questions, and I'll let you guys kind of do those or work on those after you've watched your videos. Okay. But like for the example 3, the greatest increase in entropy, again, make sure you're looking at like your state symbols, okay, and that kind of stuff, and the number of moles of gas on each side. That's kind of what you want to look for on these types of questions, okay. Okay, so here's the other part I wanted to talk about today. So the actual calculation part. So standard entropy change, which is delta S, okay. As I mentioned in earlier, and he goes over a couple examples like this in the video, but you're doing the sum of the entropy of your products minus the sum of the entropy of your reactants. That gives you the change in entropy for that chemical reaction. And so as it says here, a perfectly ordered crystal at 0 Kelvin has an entropy of 0. So they're saying if you had a perfectly ordered crystal lattice, okay, everything is entirely structured. There's like nothing's moving because we're at 0 Kelvin. Because remember, 0 Kelvin, that's absolute 0. And absolute 0 means that there is no molecular motion. Everything has stopped. Okay. And so you have to be at 0 Kelvin or at absolute 0 and have everything in a perfectly ordered crystal for you to have an entropy of 0. Otherwise, there's always going to be some way to distribute the energy, and there's always going to be a little bit of disorganization. Okay. Absolute entropy values are all positive. Okay, so notice that. So when you look them up on charts, they're always going to be positive when you plug them into this equation. So this example, and I think this is the exact one I think he does in the video, but it just says calculate the entropy change for this reaction. And so there's 2 reactants, there's 2 products, and then we have a table where they give us the entropy values. Now, on your exam, if they don't give you the table, it's in the data booklet. In the video, I think he tells you, I want to say page 12. I could be wrong. But he tells you in the video where it is. So when you're doing, like, if this was like a paper 2 question, then you could look up the values in the data booklet if they didn't give them to you on the question. Okay. In fact, they have one chart. It's on one page, or it might be multiple pages, but one chart, and they have all of the enthalpy, the entropy, and they have the Gibbs free energy values for the different things all on one chart. Okay. So I'm just gonna use that equation. So where are my products and what numbers do they have? Because I got to do products first. So I need to add up my products. So what's my first product?
Nitrogen.
Nitrogen gas. I got N2, and N2 is 192. So I have 192 plus I have water, right?
Mm-hmm.
But what's going on with the water in that equation?
You have to multiply by 2 since there's 2
Yeah.
water.
Exactly. So just like with enthalpy, if there's coefficients, you have to multiply the value by the coefficient when you put it in the equation, just like we did with delta H calculations. So this is going to be 2 times. It's been doing this today too. The iPad keeps dropping out. Let me get it back up. It's like the screen mirroring just stops for a second and glitches out. I don't know why. Okay. Let's see, is it going to come back up? There it goes. Okay, so 192 is the nitrogen. Water is 188, but we have to do 2 times 188. Okay, so then I add both of those together. Those are my products. And then I'm going to subtract, and then I have to do my reactants. Now my reactants, I'm going to switch colors. I have N2H4, which is 121, plus oxygen, and there's no coefficient, so that's just plus 205. Guess I should have left this red. So then, I mean, I'm just doing math from that point. So I have to make sure that I multiply the 188 by 2 first, and then add that to the 192. So I haven't worked this one out yet. Let's see, 188 times 2, what is that? 3 something. 188 times 2, 376. So 376 plus 192 means this side is 568 minus the other side is just 121 plus 205. So that's 326. Okay. So then I subtract 568 minus 326. So I get 242. And then I just want to make sure I put my units on. The units, though, I want you to pay attention. They're different than the enthalpy. Enthalpy is always kilojoule per mole, right? So for enthalpy, we always had kilojoule times mole to the -1. That was the units for enthalpy, the delta H. Kilojoules times mole to the -1. Notice that these, it's still per mole. It's still mole to the -1, but it's not kilojoules. It's joules. And then it's also per Kelvin because it has to do with the temperature. So the units on entropy are different than enthalpy. So it's joules, and then it's times Kelvin to the -1, and mole to the -1, because it's joules per Kelvin times mole. So that would be the answer for this one. So the entropy change is 242. So that means I lowered in entropy, right? Because I went from 568 to 326. So my entropy decreased, right? And or I'm sorry, it increased because we're doing products first. Sorry. Which makes sense because the products have so this means the products have 242 joules more than the reactants, which makes sense if you think about it, because if I go back up here on the reactants,
Miss, you're frozen again.
Yep. Okay, I finally got back in. Okay, so I mean, we were basically done. I was just going back to explain that it makes sense that the product's entropy was higher than the reactants because when you look at that equation, there was only 1 mole of gas on the reactant side, but on the product side there were 3 moles of gas because there was 2 moles of the water vapor and 1 mole of whatever the other gas was on the product side. I can't remember what it was. So just keep that in mind, that knowing that, logically the product side should have had a higher entropy. So that way, when you subtract them, your change was positive because the products were higher than the reactants. Okay. That was all I had left to say because we had already finished the problem. So that's it. Okay. Unless y'all have anything else that y'all want to add.